So our next speaker is Selim Jochim from Heidelberg University. And he's going to talk about deterministic quantum simulators for cold atoms.
So, good morning, everybody. Of course, as all the other speakers, I should also say how grateful I am to be here today, to be able to be here today, and be able to present our work, our ideas. It's really been a wonderful conference, perfectly organized, and with very fruitful discussions, which I enjoyed a lot, which I have enjoyed. So what I will be talking about is, my title is Deterministic Quantum Simulators with Cold Atoms. The systems that we are concerned with is very small numbers of atoms and deterministic numbers of atoms. Basically, systems that are prepared in a particular atom number quantum state. It doesn't work. Here it goes. So first of all, what do we want to simulate, and what would be a good thing to use? What system would be good to use? We've heard in this conference now several approaches to quantum simulation. I would just divide this somehow in two categories, and I apologize, I'm not mentioning all the different groups here, just saying, okay, there's this ion community really, and on the other hand, it's cold atoms. And what is really distinct and different about them? First of all, most of the ion systems, they have really a discrete system. They really have exact numbers of ions, as you see, for example, here. And typically, with cold atoms, we work with thermodynamic systems. However, Marcus has shown us that somehow this kind of ideas start to overlap, and he can stamp out particular systems in such a way to actually also create a discrete system with cold atoms. Then ions have the advantage of having these outstanding fidelities, both in preparation and in manipulation. And atoms, I would say, as in turn, have this possibility to tune interactions in wide ways. And then I think the biggest difference really is that usually with ions, we never talk about the indistinguishability of the particles. Normally, we would just never say whether we have bosons or fermions trapped in an ion trap, whereas this is extremely important with cold atoms. Okay, so that's one of the major ingredients here, actually. So let's take one step back. Why is this really so? Why is it really such that in an ion trap, it's so hard to see the effect of indistinguishability? Of course, we can give a very easy answer to this. Oh, wait a second. Plug it back in. Yeah, okay. So let's, first of all, you talk, hey, it's the Coulomb repulsion. Of course, Coulomb repulsion is an important ingredient here, but of course, in nature, almost all the identical particles that we look at, they're actually Coulomb repelling each other, like the electrons in a metal, and of course, we have a very large Fermi energy there coming from the identicality of the particles. So that's not really the point. Let's look at the helium atom as an example. I think this is for me, a very clean example. And it's really two trapped electrons, so it's just like an ion trap, if you want. And there, we teach our students that we typically neglect, first of all, if we try to treat the problem, we typically neglect the repulsion between the electrons, and we assume it's a good approximation, and we realize this is so. You know? And then if we do a proper calculation, we find that the ground state for the triplet, that basically the two electrons aligned, it's about 20 electron volts higher than the ground state for the spin singlet. You know? So in the helium case, so which is also two trapped charged particles, then this effect of indistinguishability of the two electrons is an enormous one. Okay? And that's very different for an ion trap, and simply because the helium atom is a super tight trap for charged particles, if you want. Yeah? That's why this really happens, and there's a very large overlap of the two electrons. Okay, now how is this with cold atoms, and why are cold atoms exciting in this aspect? we can now tune these interactions in a very large range, basically infinitely large range. We can, for example, here trap two atoms in a one-dimensional potential, and we can put both atoms, the two atoms that we have in a spin singlet state, and if they're very weakly interacting, they just occupy the lowest energy state. Yeah? And now we can make these two atoms repel each other so strongly that the relative wave function between the two particles really looks like this. Okay? And if we look carefully, it really looks like the relative wave function of two indistinguishable spin-polarized particles. And here really then also the energy of the two systems, the spin-polarized system and the spin singlet are actually really the same. You know? If I want to compare this now to the case of the helium atom, that would be the same thing as increasing the repulsion of the two electrons in such a way that this spin singlet ground state actually increases in energy so much that it becomes degenerate with the ground state, the metastable ground state of the triplet state. Okay? So this is what we can really do in experiments. We can really go from the situation where these guys are very weakly repelling each other to all the way to the case where they're infinitely repelling each other in one dimension. That's called the Ferminization. We've actually experimentally looked at this in this publication here. Okay, so how do we realize such systems? What's our approach here? And that's really, in a way, very similar to what Markus has done, stamping out a small system of a very large thermodynamic one. In our case, we don't do this in space, but we do this in energy. So, and the idea is really that if we use a proper subsystem of a degenerate Fermi gas, then we can end up with a very low entropy system. And what's basically the idea here is, this is the Fermi-Dirac distribution here plotted, the energy in the vertical axis, occupation number in the horizontal axis. And if I superimpose to a very large reservoir of filled with a degenerate Fermi gas, a very tightly focused microtrap with a very small beam waist, then the degeneracy at the bottom is very, very low. Yeah? And the only thing that's now remaining to do is to make sure I somehow can, with very large fidelity, select the highest, the lowest entropy subsystem from here, the lowest entropy particles. Yeah? That's what I'm doing here. Okay, and so what's the idea? Well, the reservoir we can easily get rid of by switching off the laser beams that form this reservoir trap. And then we still need to make sure we actually prepare a system that contains a particular number of bound states. And this we can simply achieve by overlapping with the with a microtrap beam, which is a focused laser beam, simply a magnetic field gradient, and this will result in a potential looking like this, and we just have to really make sure we actually form this potential with high enough accuracy in such a way that we have a distinct number of bound states remaining. And this gives us then a particular number of atoms, and we can actually do this kind of process as different magnetic fields, and in this way, the different states will have different magnetic moments, and we can actually have even spin up and spin down atom numbers separately determined. Okay? So this is kind of the experimental setup, a very high-resolution microscope that will allow us to focus a laser beam very tightly. That's the major ingredient. And for the experiments, I'm going to show you the typical aspect ratio of this trap is 1 to 10. That's why we can talk about one-dimensional systems for very small particle numbers. Okay? So just to show you how well this works, if you want to prepare two particles, we can do this with close to unity probability, and the same thing works also for more particles. Actually, by now, this works also quite a bit better. This was from the initial publication in 2011. So now we've been routinely working with these kind of systems and now trying to see how can we actually now go and actually model and simulate systems that we might not understand just from a conceptual point of view or just from theory. Okay? So how can we extend this system? First of all, we can think of actually realizing more than one well. Here in this case, what I'm showing you is just two wells, a double well system, and we can initialize the system in such a way that we have two particles in a single well, and then switch on the other one abruptly and observe the tunneling dynamics, and that's what you see here. What's plotted is the number of atoms observed in the right well here, and you can see very nice Rabi oscillations here if the interactions between the two particles are switched off. Yeah? Now we can dial in some arbitrary interactions, and I just want to give you a very simple example to show you how well we can control the situation. If we put in a little bit of repulsion here to the system, then this simple Rabi oscillations look completely different. But if you look at the black line that goes through the data here, that's actually not a fit to the data, but really just a prediction, knowing what the interaction strength, the tunneling rate, and also a slight tilt between the two wells is, then you can exactly predict the behavior of the two-particle system. Okay, that's not quantum simulation yet because we can predict this very easily, even analytically. We don't even need a computer for this. But it tells you how good a control we have. Yeah? And to use this kind of a building block for bigger systems, you might want to initialize this spin singlet system in the ground state of such a double well. We can also do this by simply turning on this second well slowly compared to the tunneling dynamics. And then what we end up with is a stationary state, and we can now, dependent on the repulsion between the particles, observe that is, as we go for larger and larger repulsion, we find more and more particles occupying only single wells, basically suppressing double occupancy. That's what's shown here. That's the probability for observing one atom per well, which goes up as the repulsion is increased, whereas the double occupancy is going down. Okay? And that's very much in line with what you expect from the Hubbard model for the system. So this is kind of completely understood. Okay? Now, of course, the next step here would be to try and think, okay, how can we prepare now bigger systems? Because somehow you need at least two particles with the spin degree adjusted, spin 0 degree of freedom to have like a zero entropy system if you want to merge many, many such particular systems to a larger one. And the question is, how well can one actually do this without increasing the entropy of the many-body system as one starts to couple this? There's actually some theoretical studies on this that show some favorable scaling behavior, so we are quite confident we can do this. But before I dive more into detail on this, I would like to show you some other results which you obtained only in a single well, which I think are very interesting. Okay, this I think you can just skip. And this, the point I would like to discuss here is, I told you we can increase the repulsion so much between particles that it doesn't, that the energy of the system will be the same whether you have distinguishable particles or indistinguishable particles. Okay, basically between particles of opposite spin, you can have the same energy as between spin polarized particles. And that's somehow depicted here in this picture for more than two particles, in this case 3. So the basic idea is if I have infinite repulsion, then I also should have in the relative wave function between two particles, that's a sketch which is not quite right, we should somehow depict the relative wave function which I cannot draw for 3 particles, but there should be kind of a kink in the wave function going completely to 0 between 2 particles of different spin, stemming from this infinite repulsion. And of course, because of the antisymmetry of the wave function between 2 identical spins, there should also be a 0 in the wave function for this situation. Okay? And at this point of infinite repulsion, this should then end up in a situation of a spin chain similar to a Wigner crystal where all the particles align in a chain. Okay? And so we've gotten a lot of help from many theorists here explaining us how this exactly works. And I don't want to dive too much into details here, but I just want to explain you just conceptually what's going on here. So the major point here I would like to explain again just for 3 particles, because for more particles just remains qualitatively the same thing, but one can understand the major concepts already here. Okay, so here is plotted an energy diagram where we plot the coupling strength between the particles, 1 over the coupling strength between the particles, which means that the coupling strength is infinite at the center of the plot. Okay? This is exactly the point where the energy between a spin polarized system and any other depolarized system of any spin configuration is the same. Okay? It doesn't matter how the spins are aligned. And this is exactly the reason why many different configurations, many different states of the system have exactly the same energy here at this point. So these are different orderings of the system, if you want. And now, as we tune the interaction strength here to the left, this is like minus to the coupling strength. This means here it's positive, it's repulsive, and the other side here it's attractive. So we start from very weakly repulsive on the left-hand side, okay? So that would be the non-interacting limit here is to the left, okay? And so then the lowest energy system you can have would be this one here. And here in the center, where you have this situation where all the particles repel each other infinitely strongly, you should have a density distribution of all the three particles looking a little bit like this, where if you would look at the individual relative wave functions, there should be a node between all of them, okay? And now the ordering between particles would now make all the difference at this point. And as you go away from infinite repulsion, there will be only a set of eigenstates which will be stationary states. And the lowest energy state here, which would correspond to the particles filling up this harmonic oscillator state by state, this turns out to be the one that has an antiferromagnetic order at this point of degeneracy. Okay, so this state here is really adiabatically connected to the state with antiferromagnetic order at this point. Then there's an intermediate state which has slightly higher energy, and then this state which has, which is basically has all the spins aligned, yeah, which needs basically all the three lowest vibrational levels occupied. That's the state with ferromagnetic order, which doesn't tune in energy because there's a node in the relative wave function between each particle. Okay? All these states having the same energy at infinite repulsion. That's the main idea. And now the question is, what do we actually realize when we start with a non-interacting system and we ramp on the repulsion? Remember, this is like, if I take the helium atom, going from the singlet ground state in energy all the way to the metastable state. Okay? So this is how much we crank up the repulsion between particles. And we can do this, go all the way there and go back, and we find the same system again. So what we know then is that if we start down here, we ramp up in this region here and go back, we find exactly the same system back. Which means we can do this reversibly, and the only question now that remains for us is to know, do we actually go, as we go into this region here where all the states are degenerate, do we actually populate many different states, or do we really populate exactly one? Okay? And for this purpose, we do some we try to do some determination of the state in this very strongly repulsive region. And this is here demonstrated. But we can do this for very small spin chains. We can actually just tilt the potential and remove the outermost particle. In this case, the rightmost particle remove, and we can measure whether this is a spin up or a spin down particle. Okay? And then we can do statistics and see how many times, what's the probability of this outermost particle here to be a spin down particle. And that's what we plot here. These are the blue data points as function of interaction strength. And this we can compare to a model to find out which state we are actually dealing with. And it turns out there's three different models here for the three different eigenstates of the system. And it turns out that across this point of infinite repulsion, we find the system to be in this antiferromagnetic state. Okay? This means that basically, as we start from this state down here, from the lowest energy state, we remain in this tiny dashed line across this point of degeneracy all the time, and we remain in the antiferromagnetic state. Okay? So there's no coupling to the other states because this state is somehow protected by the symmetry of the Hamiltonian. And what's really important here is that we don't really need to resolve this tiny energy scale in our experiment, and we can really work with a system that shows antiferromagnetic order here. Okay, so now the question again comes up, can we scale this up to a large system? And that's very hard to actually really make a large spin chain in this way. So this doesn't work very well, but so our major idea currently here is that we might actually couple individual of such spin chains that I've just shown you. And the smallest spin chain we can make is just two particles that form a spin singlet in one chain. infinitely strongly repelling each other, or close to infinitely strongly repelling each other, and then couple them by bringing them so close that they can tunnel. Okay? And now, as we can change the tunneling rate or the coupling along the spin chain, we can now adjust whether the situation would be such that the spin singlet would be along a particular chain or perpendicular to it, forming spin singlets in the other direction. Okay, somehow the spins don't change, but they should actually form a spin singlet along this direction. Then if the tunneling rate is increased, and this would be the dominant coupling in this system. Okay, so this is an idea we currently have, and we are super excited about this for one reason is we have another experiment. And this experiment is a 2D gas where we just starting to play with a lattice. And so the idea is of filling this lattice now, and this lattice is formed of one-dimensional tubes with a spin singlet each. And then if we do exactly this game playing with the coupling strength along the tubes versus between the tubes, we can maybe create very long-range order in such a system. Yeah? Okay, and the very interesting thing about this is if you have basically infinite repulsion along the tubes, this will be just 2 isolated layers. Yeah? But then if there's one single defect, and you sure will have that, then these defects will actually couple the layers. So that could be a really interesting coupled layer system that could be also used as a model system for many, and actually really a very interesting system for quantum simulation, I think. So now the last point I want to make, and I want to make it really short, is how would we actually diagnose such a state? You know? So we don't have such a state in our experiments yet, but we have to see and think how would we actually see what we really have. And we would really like to see, long-range correlations. We really want to like to see how an atom on the one side of the system is correlated with an atom on the other side. Okay? And how would we see this state, for example? How would we see antiferromagnetic order in such a system? So there's one ingredient that we think is important, and that is obtaining the momentum distribution. We've been very successful doing this with a bulk gas of atoms, and what we've been using here is the ballistic evolution in a very weak harmonic potential. And that basically should depict the potential here. And like several atoms distributed in the trap with the same momentum would, after a quarter period, really all show up in the same point. Really, this is the idea of momentum focusing. And it's particularly simple if we have momentum 0. Then, of course, after a quarter period, all the particles will show up in the center of the trap. Okay? So this is really an exact matter wave imaging. We are not the first ones to have invented this. We've adapted this for our purposes. And I just show you very quickly what can be done with this. This is a 2-dimensional harmonic trapped gas. And in situ, as you lower the temperature, you don't see a big effect. But as you go and look out in momentum space, so this is really a momentum space picture, you see a very stark difference in the momentum distribution showing a strong peak. And if you look carefully, this is not a peak in an inverted parabola that you're used to see from Bose-Einstein condensates, but it's more like a very sharp cusp. And this comes from the fact that we are dealing here with something like a BKT distribution. So a quasi-long-range order algebraically decaying coherence. Okay, this might not be enough, but what you really want is you want to extract more information than just coherence properties. And here we are inspired by this work here, understanding noise correlations in a system. And for this, we would like to see the fluctuations on top of the signal I've just shown you. And here we think what we can do is the following. We might get an in situ a picture of all the individual atoms in our system in momentum space by just detecting individual code atoms in free space after a time of flight. And this is really the first result we've gotten here from an individual atom imaged with a large numerical aperture lens. And this is in a picture where we detect between 5 and 20 photons after about 5 to 10 microseconds. So in very, very short time, and that's the advantage here. So we don't really need to localize the atoms in space because we don't need to image for a second or so. And we get a spin-resolved image of an atom with a resolution limit to a few micrometers, which is sufficient after time of flight. And I think we should really be able to do this with about 100 atoms or so. Okay, now the chairman is standing there wanting me to stop, and I should stop, but I would like really to thank the team here. You might have seen Vincent Klinkhammer's poster on Tuesday detailing some of the things I've been talking about, and I should maybe also mention we just got a support from a new postdoc, Philip Price, who is kind of hiding behind all the other ones, but who is now significantly contributing to progress in our lab. And with this, I would like to thank you for your attention.
Thank you very much. We have time for a few questions. Yes, Randy?
In the small 1D system, presumably the system ends up in the antiferromagnetic state because of you're going slowly enough. You're going adiabatically through this transition.
Okay.
So if you go to a higher particle number system in the 2D case that you proposed at the end, how can you go slowly enough compared to the degeneracy, which in that system is going to be huge?
So this is, of course, this was a big question for us. Now, in this particular system of very few particles, that's what we try to find out, right? We don't need to go slow compared, and that's kind of one of the essential things here that I wanted to get across is we don't need to go slow compared to the splitting of these levels, okay, which go to 0 actually, and then you would have to go infinitely slow. That's just because the symmetry of all these states is different. Yeah? And so there's no coupling. It's really a perfect crossing. Yeah? What we need to have to actually have some coupling between these levels is some spin-orbit coupling. Yeah? So we need to have some dependence of some potential with the spin degree of freedom. Then actually you could couple, and we tried actually to put in numbers. If we were to apply a very large magnetic field gradient, then we would be able to couple these states, and we should actually be able to go, if we go slowly enough, into the ferromagnetic state here, which would also be interesting. Yeah? Now, for larger systems, larger numbers of particles, that's what you asked for, there will be many limitations doing this. In particular, this is a repulsive state, yeah? And we've heard other talks already before on this conference that dealt with the fact there's also attractive states which are lower in energy, and there's some couplings to such states with like molecular bound states, and one would have to go fast across those, and that's what we need. We can still do for a few particles. It gets harder and harder as we add more particles. So I don't think it's a good strategy to try in one dimension to make longer and longer spin chains. I don't think it will work. It will be a very hard endeavor, I think.
Okay, thank you.
Yes.
Yeah, the analogy with a helium atom as a very strong atomic well is very interesting. I'm wondering how much further you can go in creating an artificial helium atom. I mean, these produce S states, but you can also have P states, D states. Can you give some angular momentum to the particles in the well?
You want angular momentum? So currently, all the systems we've been looking at were one-dimensional systems. They have, for us, several advantages, but indeed, a lot of interesting physics come in as soon as you start playing with dimensionality. You would need at least 2 dimensions. Yeah? Because you want the degeneracy of the levels. That's what you're interested in, because then you get immediately angular momentum. There's lots of, you can study quantum Hall type of physics and all these things. We are actually currently implementing techniques in the experiment that allow us to do this, and we are very much eager, actually, to go in this direction. Mm-hmm.
Yeah, and also, of course, the centrifugal barrier is another way of controlling the strength of the interaction between the particles. For high-lying angular momentum, the single triplet splitting goes to 0.
So currently, we are working with S-wave interactions only. Then this doesn't really play a role. But we had to have done some preliminary experiments. We haven't followed up on this. Playing with P-wave Feshbach resonances, and this way creating P-wave molecules, P-wave bounces, and then what you're saying is actually very interesting. And this also would be something to look at in these kind of systems, yeah? Which is otherwise very hard because of collisional instability.
Okay, thank you. So our time is up. So let's thank Selim again and all the speakers of this session.
Okay, the session ends on time, so now we can have a 25-minute coffee